Hello, we are completing chapter 11 with part 2 here in this video. I'm going to discuss elimination reactions, both E1 and E2. We had said in the beginning of this chapter, when we were talking about substitution reactions, that um, the species like OH minus can not only act as strong nucleophiles, but they can also bring about elimination reactions because they can also behave as bases. Okay, so we can actually look at this particular reaction here, which is an alkyl halide, again, which is your substrate. Substrate is the molecule on which the reaction is happening, and OH minus is acting as a base here. It is helping to remove the hydrogen here, that is a proton, and then the Br minus is also removed. So this reaction results in the formation of an alkene and the side products being water and bromide ion. This is an example of an elimination reaction. Now, elimination reactions can be a little more complicated than substitution reactions because we have to look into what is called as the Zaitsev's rule for predicting the products of the reaction. Okay? So according to Zaitsev's rule, this is Zaitsev's rule, the product of an elimination reaction would be the one where there is a greater substitution at the alkene, or you can say the major product would be the one where it's a greater substitution at the alkene. Okay, here if you look, there are two products. Maybe this is more clear when I draw it out as a skeletal structure. The one of the products is this, and then the second product is going to be this. Okay, so there are two ways by which the elimination can happen from this molecule. One is the 2-butene, where it is more substituted at the double bond. See, these are the two carbon atoms and both have one substituent, and here these are the two carbon atoms which form the double bond, and there is only one substituent here. Okay, so you have a mono substituted alkene and a di-substituted alkene, and according to Zaitsev's rule, which you have studied in chapter 7 regarding stability of alkenes, that the more substituted alkene would be the more stable one. Similarly, if you look at this one, this is a 2-bromo-2-methyl butane, and you are reacting it with a base. The base is the sodium ethoxide. We can see that a major product is where you have more substitution at the double bond than the one which has got less substitution. Okay, so this is how it's drawn. This is 2-methyl-2-butene. So we have the double bond here, and in this case, the double bond is over here, and then the methyl group is over here. So the 2-methyl-1-butene product would have only one substituent, whereas the 2-methyl-2-butene has actually three substituents, right? It's a tri-substituted because see, there is 1 and 2, and then there is a third substituent. So this becomes your major product. So you have to make sure that while predicting the products of elimination reactions, you have to keep in mind the Zaitsev's rule, but then you will also see that when we are talking about elimination E2 mechanism, you also have to make sure that the product is following what is called as the anti-periplanar geometry. Okay, we'll talk about that in a bit. In E2 elimination, just like in SN2, okay, it's a concerted step. Everything happens at the same time. That means the attack of the base to the proton, formation of the double bond, and removal of the leaving group. They all happen in one single step. That's why it is called as a concerted reaction. You need a strong base. That's important for E2. You need to have a strong base. Elimination reactions are also accompanied with heat. That also helps to increase the rate of the reaction. Strong base removes the proton. Double bond is being formed, and the leaving group is removed. So, for example, if you are asked to predict the product of this reaction, you have to keep in mind the Zaitsev's rule. This is a strong base. Strong base. Here is your elimination, the leaving group, chloride. And then the hydrogen that is removed, we call it as the beta hydrogen. Okay? Beta hydrogen means the hydrogen that is next to the carbon atom where the leaving group is. So if this is the carbon atom that has the leaving group, we have beta carbon atom which is this one. There is another beta carbon atom here, and this is a beta carbon atom. Okay, so the hydrogen attached to these pink colored carbon atoms, that is called as the beta hydrogen, and the elimination happens with the removal of the hydrogen at any one of these carbon atoms that I have marked in pink in color. Okay, so this will result in, so if the hydrogen from here is removed, okay, so let's draw the hydrogen here. If this is the hydrogen that is removed, you will get the product which will look like this. So remember that it is all a concerted step. So the chloride is removed, the OH removes the proton, and the double bond is formed, right? So the product would be where the double bond is formed here, and you have a CH3 here. Okay? Or if the hydrogen atom on this methyl group is removed, then the product would look like this. The chloride is still removed, and then the hydrogen from this carbon atom is removed, so you will get a product which looks like this. Okay, one is a di-substituted alkene, and this one is a tri-substituted alkene. Okay, see the carbon atom, you have 1, 2, 3 substituents. Here you have only 2 substituents, so this is di-substituted, and this is tri-substituted. So the tri-substituted alkene will be your major product following the Zaitsev's rule. So to look at the correct product here again one more time, reaction of the alkyl halide, which is your substrate, with the strong base like potassium hydroxide, you can get major product as 1-methyl cyclohexene and then minor product as methylene cyclohexene. Okay. To look at the mechanism of this reaction, this is how it happens. The base removes the proton, formation of the double bond, and again look, this hydrogen is the beta hydrogen, beta elimination. We call this as beta elimination, where the hydrogen atom and the carbon atom next to the leaving group is the one that is removed, and then the leaving group is removed at the same time. This is how the transition state looks like. The bond with the base is being formed, the bond or carbon-hydrogen bond is being broken, the carbon-carbon double bond is being formed, and then the carbon-halogen bond is being broken. And it results in the formation of an alkene. Okay. So the important features of this E2 elimination is that you should have a strong base. Okay, you definitely need a strong base, and also a tertiary carbon atom or an alkyl halide is more reactive than a secondary, which is more reactive than a primary. Okay, in case of a substrate choice, preferably to have a tertiary alkyl halide is better than a secondary, which is better than a primary. Okay, so the reason is that when you have a tertiary carbon atom, then the formation of the major product following the Zaitsev's rule is applicable. So, for example, if we use this as the example here, say I have an alkyl halide like this. Okay, a tertiary alkyl halide. And let me draw the beta hydrogen atoms. So this is my beta hydrogen atom. I have a beta hydrogen atom here and beta hydrogen atom here, which is kind of the same, right? If I do an E2 elimination here with a strong base, so base can remove the proton with these electrons here, and the leaving group is removed, correct? So you can see that the formation of the major product is this. Okay, so the minor product would be this one, where the double bond is formed over here, which is only a di-substituted. This is a tri-substituted, right? So if the base removes one of these hydrogen atoms, then you'll get the minor product. Let's take the example of a secondary alkyl halide. Okay, so say for example I have a secondary alkyl halide, which is this one. Now if you have the same base, which is going to remove the beta hydrogen atom, the beta hydrogen atoms here are this one and here. Okay, let's put a color on here. So pink colored ones, these are the beta hydrogen atoms. Now in this case, if the base removes the proton from here, then put the electron here, chloride comes out, you will end up in the formation of a disubstituted, and if the base were to remove one of these hydrogens, then you would result in the formation of a monosubstituted, right? So it's always seen that when you use a tertiary alkyl halide as your substrate, you will always get the more substituted alkene, which is the more stable alkene. Whereas for a secondary or even for a primary, you get the less substituted alkene. Therefore, the tertiary is preferred substrate than a secondary, which is a preferred substrate than a primary. Which is kind of opposite to that what we see in SN2, because in SN2, we saw that a primary is preferred more than a secondary, which is more preferred than a tertiary. Okay, so that's one difference between E2 and SN2. Both of them need strong, like one of them needs strong base, and the other one needs a strong nucleophile. But the trend for the use of base, so the substrate is different in case of E2 and SN2. All right. Another factor about E2 reactions is that they prefer to have, the substrate should have anti-periplanar geometry with respect to the hydrogen and the leaving group. Okay, so in an E2 elimination, the reaction occurs with a anti-periplanar geometry in which the H and the X, okay, the H and the X that are going to be removed. X is the halogen atom, hydrogen is my beta hydrogen. They are required to be in anti-periplanar geometry. That means the hydrogen and the leaving group should be on opposite sides of the molecule. Okay, so it is energetically preferred to have a anti-periplanar. See, this is an anti-periplanar. The hydrogen and the X, the leaving group, are in opposite sides of the molecule. This is an example of a syn periplanar. This is a syn periplanar, but this geometry is not preferred for an E2 reaction. So you must be wondering what is so special about this anti-periplanar geometry, right? So it is seen that since the sp3 sigma orbitals in the reactant CH, okay, the CH and the CX bond must overlap. See, if you see in the transition state, you have to have the sp3 orbitals in the reactant CH and the CX bonds to overlap. Even in the transition state, there is some overlap. So the best geometry that makes the maximum overlap is when they have the anti-periplanar geometry. Okay, so that is why it is preferred, so that you can get the product which is your alkene. Similar to, you can think about this similar to the SN2 reaction, where the electron pair from the incoming nucleophile needed to be almost 180 degrees while doing this backside attack, and then the leaving group is in the opposite direction. So similar to that, we can think for this E2 reaction that the electron pair from a carbon-hydrogen bond also pushes out the leaving group on the opposite side of the molecule. Okay, now we can look at examples of how this anti-periplanar geometry can have implications on the formation of the product. So look at this example here. We have a meso 1,2-dibromo 1,2-diphenyl ethane, and this one has an anti-periplanar geometry. Hydrogen, the hydrogen and the bromine, they are on the opposite sides of the molecule. Base removes the proton, formation of the double bond simultaneously happening, and then leaving group is leaving. Okay, results in the formation of a E alkene. Okay, so if you recall from chapter 7, we did this E and Z nomenclature, where here you can see that the E alkene is the major product. So you do not get the Z alkene here, which tells us that Z alkene would have been formed if the syn periplanar geometry were there, right? You do not see any of the Z alkene that is formed, which tells us again that the syn periplanar geometry is not the preferred one. Okay? Let's look at another example here. This is with a cyclohexane, cyclohexyl halide. So we have a chloride here, and then again remember that beta hydrogens are the carbon atom next to the leaving group's carbon. So these the ones that are marked in blue. These are my beta hydrogen atoms. Again, you could have removed this or this as they are anti-periplanar. See, you have the hydrogen and the chlorine in the opposite side, or you can have this hydrogen or chlorine in the opposite side, and you could get the formation of a E2 product. But in this case, we are saying that if the chlorine was in the equatorial position, now this chlorine is in the axial position. However, if the chlorine was in the equatorial position, no reaction is seen in this conformation is taken, because the chlorine is not an anti-periplanar with the hydrogen atom. Okay? So it looks like you need to have the axial positions for the leaving group and the beta hydrogen atom in order to form the product for an E2 elimination reaction. Another example is shown here where you can see that it violates the Zaitsev's rule actually, because of the fact that the chloride and the hydrogen which are removed can only take this position as shown here to form the less substituted alkene, whereas you can if it were in a trans geometry here, they wouldn't have been able to have that anti-periplanar geometry, and you wouldn't get the compound that is shown here, 2-3. Okay? So these are all important aspects of E2 elimination. Next is E1 elimination. So before that, let's kind of summarize what we looked in for E2 reaction. Let's put a new slide here. So first thing, in E2 elimination, it is a concerted reaction. Actually, we didn't talk about the rate here. Similar to SN2, we can say that the rate is dependent on the substrate, which is your RX, alkyl halide, and also the base. Okay, it is dependent on these two things because it's a concerted reaction. Okay, or you can remove the proportionality sign here and say K, RX, and base. However, just like in SN2 reaction, the alkyl halide and base, even though they are important in the rate, the trend for the substrate is different from SN2. Here, actually, we prefer a tertiary better than secondary, better than primary. Okay, so regarding the substrate, this is what is preferred for an E2. The third thing is this requires a strong base. If you talk about leaving group, just like in SN2, you need to have good leaving group. So the leaving group propensity is still the same. Iodide is better than bromide, which is better than chloride, which is better than fluoride. Okay, and then finally, in case of the solvent for E2 reaction, polar aprotic is preferred. So just a lot of similarity to SN2 reactions. Like in SN2, the only trend that is different is this substrate trend. Okay, otherwise you need a strong base, good leaving group, and solvent is polar aprotic, just like in SN2, and even it's a one-step mechanism, concerted mechanism, as if you recall from SN2. Now let's see as E1 reactions. Now E1 reactions are similar to SN1 reactions, okay, where the first step is the formation of a carbocation, which tells me that here also, just like in SN1, a tertiary substrate is preferred than a secondary, which is more preferred than a primary. Okay, so the substrate trend, preference is the same for E1, E2, and SN1. So that's why when we try to predict reaction mechanisms, sometimes you will see that SN1 and E1 reactions happen hand in hand. That means you will see both E1 and SN1 products because the reaction conditions are pretty much similar to both of them. So just like in SN1, the first step is the removal of the leaving group, formation of a carbocation, and base comes and removes the beta hydrogen atom to form the product. Okay, so pretty similar two-step mechanism. Here again, if you were looking at the rate, it will be only dependent on the substrate. So we prefer it to have a tertiary than a secondary and then a primary. Regarding the mechanism, one more time. So you can see that this is my rate limiting or the rate determining step, the first step, formation of carbocation, and then the base removes the proton from the neighboring carbon atom, which we call it as the beta hydrogen, to form the alkene in a fast step. Now here you do not need a strong base. A medium or a weak base is okay, just like in SN1 where a medium or a weak nucleophile would have been okay. Similar to that, a medium or a weak base works good for a E1 reaction, and you can see that the product is formed here. Okay, so that's why here, as I was saying, that sometimes this is an SN1 product, right? So you had replaced the chloride with a OH. So SN1 and E1 products are generally formed in combination when you use a tertiary alkyl halide and the weak base, which can also act as a weak nucleophile. Now, this is an example which is comparing E2 and E1. We can see that under E2 conditions, this reaction formed 2-menthene because of that anti-periplanar condition. For E1, such a condition is not required. You do not require to have an anti-periplanar geometry. So in this case, see, even in this configuration where the chlorine is in an equatorial position, you still could have got the products here, where you can see that the more substituted product is the major product, whereas here the less substituted product is the major product due to the requirement of that anti-periplanar geometry. So that's the difference between E2 and E1, that E1 does not require any anti-periplanar geometry for the starting material, whereas the E2 condition requires that. Even though we are using the same base in both conditions, here we get the more substituted product as your major product, and here we get the less substituted product as the major product because of that requirement. Okay. Now this is an example where you are asked to use your knowledge of all the 4 reactions to see if you can predict the product of these reactions. So when you have a question like this, the first thing you should check is what kind of substrate you have. Here is a secondary, right, which kind of tells us that it could be any one of them, right? The substrate is not giving us any idea whether it is SN1, SN2, E1 or E2, because it could be any one of them. So we go to the next step and check the base or a nucleophile. Okay, and in this case we see that we have a strong base which can also act as a strong nucleophile, right? And then the solvent, right, is telling us that it is a polar protic solvent, right? So for an SN2 we prefer to have a polar aprotic, but in case of E2 you can have a reaction with the polar protic solvents also. So here the E2 reaction is predominating, so you may get a minor product of your SN2 here, but the major product would be that of an E2 elimination reaction where the base will remove the proton from here. Okay, so if you write the mechanism, this will remove formation of double bond and removal of this, and E2 is a concerted step So all of them will be happening at the same time. Okay. The next one is a benzylic carbon atom or a benzylic halide, and here we have a uh, formic acid, which is a weak nucleophile and also a weak base. So that's why you will actually get both SN1 and E1 product, where it can act as a nucleophile as well as a base. Okay, so if it is acting as a nucleophile, then it will remove the bromide and put the formate ion here. Okay, formate as the nucleophile. And if it were to act as a base, then you only have one beta hydrogen. Oh, sorry, the beta hydrogen is on only one side of the carbon atom here. The other here we do not have any beta hydrogen atoms. So if you remove that, you get the E1 product. Okay. So there are plenty of worksheets and resources which have been posted on the D2L for you to practice. So most of your reactions would be where you have to predict the mechanism of the formation of the product, whether it is E1, E2, SN1 or SN2. So always consider first the substrate, then you go to the nucleophile or base, and then finally the solvent.